Okay, so we're going to get started with our next talk. We have Jamey Sharp, and he's going to talk about hardware-accelerated graphics on microkernels. So please go ahead.
All right. Yeah, so I'm Jamey. I work at Galois, which is a small, high-assurance software company in Portland. So we do safety-critical or security-critical software, trying to bring trustworthiness to the software that we are trusting. The title of my talk is Hardware-Accelerated Graphics, which you all know a lot more than I do about, on microkernels. And so I'm going to start with what's a microkernel, just for a little refresher. So if you look at Wikipedia, it says this is the near minimum amount of software that can provide the mechanisms needed to implement an operating system. So in X, we talk about policy versus mechanism. This is sort of if you do that to your operating system. What is the smallest amount of mechanism you can provide in the kernel that lets you build all the policies you care about on top of it? So there's Wikipedia is full of nice pictures for this. So if you think about the way Linux or Solaris or BSD, any of these work, the kernel has a ton of code in it. The Linux kernel has 13 million lines of code according to slot count. It's got your file systems, it's got your scheduler, it's got your virtual memory, all your device drivers, all this stuff is there in kernel space, and then you've got your applications out in user space. In a microkernel setting, you try to keep as little code in kernel space as possible and do as much in user space as possible. So you probably need a scheduler. You may not need any kind of memory allocator even. You may be able to push all of that memory allocation policy into user space. And you need some communication mechanism between processes. That's kind of it. You might need something like a timer to make the scheduler work, but it's going to be a very small amount of code. But why does anyone care? Microkernels have been traditionally kind of a academic's folly. In the great Tanenbaum versus Torvalds debate, we've got Torvalds on the side of industry, right, and Tanenbaum as a professor on the side of the academics here. But why do the academics like this? Why is this interesting? And it largely comes down to I do not trust Linux or any other kernel, right? It's this giant pile of code. We know it is full of bugs. We see bugs appear in it all the time. In a microkernel setting, it's small enough that you might actually be able to verify that it actually does what it's supposed to, and that it doesn't do things it's not supposed to do. So, for example, folks at NICTA in Australia built this SEL4. It's 9,000 lines of C, so much smaller than the 13 million lines in Linux kernel. And it's formally verified C. So they spent 11 person years proving these 9,000 lines of code correct. And that proof tells them that their code won't invoke undefined behavior in C, it won't overrun any buffers, it won't write through pointers that point to random places in memory, and that processes built on SEL4, you can actually rely on them, rely on SEL4 to enforce isolation between those processes. So now you can have both trusted and untrusted code running under SEL4, and SEL4 will guarantee for you that the untrusted code can't interfere with the important stuff. I think I have enough time to go into a brief side story here. At work, we've been doing this proof of concept high assurance quadcopter autopilot, which has very little to do with X. But the interesting thing was part of the demo involved using SEL4 to run a Linux VM in one partition under SEL4 and run some trusted code directly under SEL4. And we gave a red team whose job was to attack our work We gave them full root access to the Linux VM. They could do anything they wanted in there. And they were not able to find any way to escape that VM. There were no security bugs that they could find that would let them interfere with the behavior of the rest of the system. So this is the kind of isolation that I'm looking for. Like, would you actually trust Zen or some other system? Do you actually believe that you will not find any such way of escaping the VM in any of these other systems? I mean, I don't. Now, there's a cost to this kind of formal verification as performed on SEL4. The NICTA folks estimate, I think the number was $126 per line of code if they were to try to redo the work given the tools that they built in the process of building SEL4. If you multiply that out by the number of lines in the Linux kernel, that gives you an estimate of like $1.5 trillion. To do the same thing for Linux, this is an optimistic cost estimate because this is probably not actually a linear scalable cost. It may actually be exponential or something, but let's assume that. That's 10% of the annual US gross domestic product. But on the other hand, it's only about 3 times as much as slot count estimates with its COCOMO model of how much it should cost using traditional techniques to build the amount of code in the Linux kernel. So maybe this isn't a completely insane approach. But of course, SEL4 is not the only microkernel out there. There's a long history of these research microkernels. Another interesting one is the Nova, they call it a microhypervisor, a super awkward name. And the demo I'm going to give a little later is actually running on Nova. So a microkernel is an interesting thing. I hope you will at least agree that it's interesting, even if it's not practical. But it only goes so far. So it's a microkernel. There's no drivers in the kernel. Where do you get your drivers from? Historically, what's happened is every one of these research microkernels has just had to write their own drivers. So you've got all this work done when all the researcher actually wanted to do was go say, well, I've got this new idea for IPC, let's try it out. And now they have to go write a bunch of drivers, which was not in their research area at all. And so you wind up with all these dead research projects because of course nobody's going to use it, it's got no drivers. And this is a really unfortunate thing for this area of research. So there's this project called Genode, which is trying to produce a portable user space, including device drivers, portable to a bunch of different microkernels. They actually have over a half dozen different microkernels that you can build and run all of their code on. And in this project, they've got support for x86 and ARM. They have some basic frame buffer and input drivers, basic stuff for sound and block and network and USB and serial, and a handful of file systems. So it's not anywhere near the level of driver support that you expect on, even just supporting all of the laptops in this room, right? But it's something, and it gives researchers a better place to start. They also have a variety of things, partial POSIX-ish libc. They have support for building Qt apps. So you can take a bunch of existing Linux software or other free software and build it on this system and try running it on these microkernels. And finally, you can run a VM like VirtualBox on at least some of the microkernels, all tied into the whole Genode setup. So there are a handful of brave souls who are now actually running Genode as their primary desktop, except that they're totally cheating because all the actual work is done in a Linux VM running under Genode. So this is the X.Org Developers Conference, so let's actually talk about graphics. Let's think about what a microkernel-friendly graphics architecture would look like. But first, here's a nice diagram of the Linux graphics architecture, and I'm focusing here on OpenGL. And what I particularly want to draw your attention to in this diagram is that libgl and the majority of the hardware-specific code in Mesa is all in the same address space as the application. And when you make your GL requests, Mesa goes to some trouble to not have every one of the function calls you do immediately transition into the kernel. You want to batch things up. You want to do all sorts of things. So so there's this notion here that that transition between your application that's deciding what to render and your kernel that has direct access to the hardware, that transition is expensive and you don't want to do it too much. So what would a microkernel graphics architecture look like? Well, I'm going to argue it would look a lot like what we already have in Mesa. Only you sort of turn it on its side, right? Now you've got the DRM code in userspace, but in a separate process. So only that process has access to the hardware. You do a cheap IPC, just briefly passing through the kernel to tell the DRM code what to do next, and you've still got all this this structure of batch things up in Mesa and try to do as much work as possible there, and just quickly hand things off to the DRM code. So this is neat. This idea that maybe what we've got is already almost the right thing. That led to, in 2010, Norman Fesky of Genode Labs said, well, I'll try taking the Gallium i915 driver and I'll drop it into Genode and see what happens. Now, he did it in a kludgy proof of concept way. So you start by doing the same sort of thing that the Solaris folks have to do, and I suppose the BSD folks have to do. If you wrap the driver in a pile of compatibility glue, nobody likes that very much, but that's where we are. It gets a little worse because then what he did was he shoved the i915 code into the same address space as Mesa, just linked them together as direct function calls. So now your GL client actually has to have direct access to your hardware. Clearly that's not the desirable thing to do, both because it doesn't actually buy you any security and because it means that they could only have one GL client running at a time. So two reasons why this isn't actually what you want, but interestingly, you didn't actually have to make any changes to Mesa, and much of the kernel code is reusable directly, and this gives a clear path to what a real graphics architecture on a microkernel might look like. I was hoping to actually build that real graphics architecture and be able to demo that, but I hadn't managed to pull it together in time. So I will give the brief demo, assuming I can do this successfully. I found a Dell laptop that was old enough to still have Intel 945 graphics so I could run the demo from 2010, and also had a serial port so I could verify that it was actually hardware accelerated using the console output. So here we're looking at this Windows system is called Nitpicker. It's the GUI that the Genode ships by default. And if the mouse button would work. Okay, and now we see how long it takes me to reboot this machine, which is actually not very long. While I do that, are there any questions?
Was graphics architecture how they've done it?
I'm sorry, at the which?
For Apple?
Apple's graphics?
Yeah, they've got a microkernel, right?
Oh, so the mock microkernel used in underneath a wacky BSD layer in OS X is what you're asking about, right?
Yeah.
Well, that figures. No, I haven't looked at how they do their implementation. But I assume that it's much like most of the stock OSs. I mean, most of the OS X is a little weird because although they have a microkernel underneath, they then have this whole other kernel on top of it that's still running in kernel mode.
I wondered, if they cheated or they...
They cheated a lot.
Okay.
A more interesting comparison is actually with Windows NT, which, as I understand the history, was originally designed to be a microkernel, and I believe had all the graphics drivers in userspace, and then they had performance issues. So over time, they kept migrating more and more things into the kernel, and there we are. There's a question.
Another fairly important microkernel is QNX.
Is that QNX? Or?
Yes.
Okay. I don't actually know anything about that.
Yeah, it's a microkernel, but I mean, it was first built in the early 80s, so it might have grown since then. If you know how software is.
Yeah.
But it's used in the automotive world, and it's used in BlackBerries. It's the new BlackBerry system, not the old one. That's the one they made the transition to with BlackBerry 10.
Okay.
And
There's
least
also, I guess, more than 1 billion phones running the predecessor to OKL or to SEL4. It was called OKL4.
don't know that one.
Yeah, it's not a lot of people have heard of it.
Feature phones or?
I think feature phones, yeah. Well, apparently when I switch the projector on, the GL rendering stops.
You were having projector issues earlier. So.
I was having dramatic projector issues earlier. Well, that's demos for you, I guess. I had actually tested this with a monitor in my office, but something is different here, I guess. It's not super surprising. This was hacky code to begin with. Yeah, so as I said, I work for Galwa. The project that I'm talking about here is Genode. If you're interested, genode.org. Any further questions?
So how do you make a secure operating system and then suddenly add a GPU? Like the GPU itself would make kind of the verification kind of moot, right?
So DMA,
it's not moot, but
DMA is really the big concern, right? And of course, you're not going to do hardware accelerated graphics without DMA. So yes, absolutely, that is an interesting question. But it's one that we care about broadly anyway, right? I mean, we have the same sorts of concerns with DMA in Linux. Hardware vendors are moving towards hardware solutions for this, IOMMU and VT sorts of things. Looks like Adam wants to add something.
Yeah, without IOMMUs, I don't see how it could work.
Even with IOMMUs, you're assuming that the implementation of the code that manipulates that IOMMU not only is correct in a formal C sense, that you're writing the bits there correctly, but that the device believes you, right? And if you, what was the name of the Rowhammer hack that was recently done, where like it turns out that if you refresh adjacent lines of memory too often the wrong way, that you can just write arbitrary crap. So yeah, there's a lot of formal verification that can happen, assuming the software implements what you told it to.
Well, Rowhammer isn't a software problem, right? It's a hardware problem. But
okay.
Yes. So at every layer, you know, you can have concerns at every layer.
Yeah.
I'd like to advocate here is that right now we have crap everywhere. And that doesn't mean that we shouldn't try to fix some of the crap, right?
We're trying.
Other questions?
Anyone else have a question?
Well, I guess we'll have a long break.
Great, thank you. All right, so we'll take a little break. Our next talk will be at 3:45.
So the difference between at your office and here is witnesses.
Yes.